Does anybody have any questions before we move on to the rest of this homework on homeworks 1 to 3, the first half of homework 4, class procedure, the exam, the forthcoming exam, that kind of stuff? I want to talk about those things before we jump back into the homework. Were you motioning for attention, Taylor, or were you stretching? Stretching, I guess.
I was actually searching for the link in the email that you had sent to the recorded videos.
Oh,
that was that motion.
I see.
Just
So
to make sure.
Find it, or do you need it still?
I'm looking right now.
Okay. If you have trouble finding it, I'm sure I can send it to you.
Okay. But
Yeah,
continue,
so all of these are every single class we've had, I think, except for the class where we practiced doing where we practiced screen sharing between us, is now on YouTube. And the whole class is there, including whatever was on the screen when we were doing it. So if at any point you realize some old problem doesn't actually make sense to you, you may go back to those videos and fast forward to them and find the appropriate moment and re-go over those derivations if you think it would help you. And if you miss a class for any reason, that is absolutely what you should do to help catch up. And they're all there, and they all will be there, and at least until the end of the course. I will probably take them down once the class is over, mostly so that you guys don't have your images on the net forever against your own will. But while class is going, I'm going to leave them there so that you all can play or review, so to speak. Other questions? Okay, let's get back to homework 4 with problem, it looks like problem 11, and we'll start with Christopher. You got this. There you go.
Okay. So I hope I set this up right.
Yeah.
Essentially, what we're trying to do here is describe the expected number of nucleotide differences
Yeah.
for question number 10.
Or 11, I think.
Or, so,
You're on 11. I'm sorry, whatever I said, you're on 11. Yeah. But from problem 10. Yep, you got it.
Yep. And so I guess I believe from problem 10 we determined that that this right here, this equation,
Yep.
was essentially the probability
Yep.
of any single sorry. Yeah. Anyway, so then you essentially kind of turn this into the mean. So you you sum up for any expected number of nucleotide differences, you sum that up, multiply it by that number, and divide it by.
So let's talk about this just very slightly. So the way the first thing to say is when you multiply by the probability, there's no dividing by k. The reason you associate dividing by k in a expectation is because you're used to a case where they all have equal probability. So there would just be no k there on the bottom. Oh, look at all that beautiful LaTeX, or something resembling LaTeX.
Right. So So it would look more like this. Is that
Yes.
correct?
And the values of k that are legal are every value between 0 and infinity. So this sum, I would simply make I equals 0 to infinity of theta over 1 plus theta to the I times I.
Right.
So I would write that as this thing raised to the I power, and have I go from 0 to infinity rather than over the finite sum. Yeah.
I see. Okay, cool.
And then multiply it by I there rather than k sub
Oh,
I.
right.
Yep. And have that thing raised to the I as well rather than the k sub I.
Sorry, like that.
I can't touch it. No, I would have it
Oh.
read.
No, I get it. I get it. Yep. Like that.
Yep, something like that. Let's see what it looks like now.
Is that coming out now?
Oh yeah, that's beautiful. Yeah, that's exactly it. That's exactly what it should look like. Yes. So that is the definition of the expectation. And that is probably not solvable in an elementary way to you. Like it's probably simply not solvable. But it turns out, you're going to have to trust me on this one, that sum is equal to theta. Right there, that sum is equal to theta, full stop. And that is a geometric distribution. And so one of the ways you might have learned that this sum was theta is because if you had known it was a geometric distribution, you could have gone and looked up the properties of a geometric distribution. And so when I did it, because I'm stupid and lazy, I just said, I know that's a geometric distribution. And when I look up a geometric distribution, I look up a geometric distribution and discover that the mean is equal to h over g in this case. So I did nothing more than I said, this is a geometric distribution. I then went to Wikipedia or something similar, looked up the mean of a geometric distribution and came up with h over g. And then I did a little bit of algebra and showed that h over g was theta. Does that make sense to everyone? So
I guess I'm not following. So when I look up the geometric expectation, it's 1 over p. Is that different? Or how do you get from that?
no, it's not. Because you have to be very, very careful with how someone defined a geometric in terms of what is the first value, like is 0 a possibility? Is 1 a possibility? And what is the probability of getting 0 and what is the probability of getting 1? So, right, because the geometric has the form g hat over h to the k, where g is 1 minus h, you can imagine starting to make other geometric series where the first g is equal to g hat times h. And like you can, and it goes not from 0 to infinity, but from 1 to infinity, and stuff like that. So in order to like use an off-the-shelf definition of what the mean and variance is, be very careful that whether the sum goes from 0 to infinity, goes from 1 to infinity, goes from 2 to infinity, and whether and making absolute sure the two terms add up to 1. So I'm almost positive you used a form of a geometric that existed from 1 to infinity. And it's probably, so yeah, it's something like that. But we'd have to look at it to get it quite right. But the whether we call one of them P and the other Q and who we call P and Q, it looks like it is the term that gets part of the geometric series on the top in the first term, the K0 term on the bottom when it goes from 0 to infinity. So yeah, that is a tricky thing about what a geometric distribution is. It will be defined slightly differently by different people in different contexts. And, you know, and all of them are fundamentally the same in the sense that they're using, right, you guys all know the number of terms between 0, 1, 2, 3, 4, and infinity is equal to the number of terms between 1, 2, 3, 4, 5, and infinity. Between 5, 6, 7, that all of those infinities are countable and they are the same size. So you can start making transformations of things that start at number 0 and go to infinity to things that start at number 1 and go to infinity versus, and depending on who created the geometric distribution you're looking at, they may have had good reason for it starting at 1 or starting at 0 or starting at -1. You got to pay attention, that's all. But if you start at 0 and it looks like p times q to the k, that's going to be your mean. Does that make sense? Okay. Up next is Yangshi with the variance. Is he on? I thought he was on. He's not on. Yeah, there
I
he
was
is.
having problems finding
Yeah.
the Zoom anyway. So I just took the notes from class and
Yep.
I wrote it down.
There
So
you
the
go.
variance, yeah, the variance is just the variance of a geometric distribution.
Yep.
And that's just h hat over g hat squared. But if someone else actually did the problem, maybe that would be more insightful than just showing what this is.
Hey, did anybody derive these? Yeah, I should have actually asked. That would have been the smarter thing to do. Did anyone bother to, did anyone actually derive the expectation of a geometric or the variance of a geometric? Yeah, too much work. The answer is you're going to use a moment generating function, or you're going to use an argument very similar to the construction of a moment generating function, which involves some sort of internal kind of integration and differentiation to make things suddenly appear like expectations and be something that you can actually integrate to solve. But okay, doesn't really matter. For our purposes, because we know how to look up things in books when they are simple things like geometric distributions, we've learned that the mean of this distribution is theta, and the variance is theta times 1 plus theta. And you should keep that in your head forever. If you look at two sequences, how many differences do you expect? Theta. What's the variance? Yeah, theta squared. In fact, theta squared plus theta. So the variance is considerably bigger than the mean. In fact, it's bigger than the mean squared. And as a result, your intuition is, even though this is not a normal distribution, but your intuition is for two sequences, even if I expect a lot of differences, I shouldn't be surprised if I see very few. That because the variance is quite large in comparison to the mean, the notion that you see 0 differences will never be all that surprising to you. In fact, the mode of the distribution, the highest point in the distribution, is 0. So the most likely outcome is you see 0 differences between your two sequences, even when the expectation is that there's quite large numbers. And that is true for any neutral model that has no recombination in it. Once you start adding recombination, the variance starts going down. But until you add recombination, the variance in the number of differences is very, very large. We haven't defined what we mean by recombination recently, but anyway, for neutral sequences in the absence of recombination, pick two people, average number of differences theta, the variance is theta squared or bigger, so that you can get any number really between 0 and quite a bit bigger than theta, and not be surprised. Questions about this? Up next is Young Xian with the maximum likelihood estimate.
Let me share. Okay, am I sharing the right screen?
Okay.
Yep. So the likelihood of a parameter theta can be defined as the probability of data given the parameter, which is theta. And the maximum likelihood estimator is gonna be the estimator that makes the likelihood maximum. So given theta equals 4 nu, because I used 4 nu throughout the problem, like 10 to 12.
Yep.
The probability of having k nucleotide sites that two sequence differ is theta over 1 plus theta to k times 1 over 1 plus theta, which is from problem 10.
Mhm.
And the theta makes this formula is going to be the maximum likelihood estimator. And I get the graph to see where the maximum likelihood going to be. And then I see that this function is kind of increase a little bit and then like decrease again. So the theta that's going to make this formula maximum would be the theta that make this like slope of this graph to be 0. So I solved this one. Oops, I lost this formula, but it's gonna make the theta equals k. I'm missing like very last part of the
I
like
understand.
solving, but yep.
So this is both a very good intuition and a very good derivation. So if you scroll up to your picture, the picture would probably be a little easier to read if you only made theta go from 0 to numbers big, because you know theta has to be positive because it's 4 times a positive number times another positive number. So you could restrict the picture to the positive side, so I don't see this distracting nonsense.
Yep.
But you are absolutely so what you did is you set k equal to 1, and by God, it looks like it takes a maximum right at k equals 1. Probably does.
Mhm.
And so you then prove that. And the way you prove that is, the slope is going to be 0 there. You differentiate the function with respect to theta, and then do algebra. And it is nothing more than algebra from the moment you wrote down that differential to the end of the, I don't really care what that display style was supposed to be, but eventually it is going to read theta equals k.
Yep.
And that is just absolutely correct. And it is, and it's just nothing more than doing a differential and some algebra. Did anyone else do a slightly different version of this differential to try to make the algebra a little cleaner?
Yes, I use log differentiation because I didn't want to use the quotient rule a bunch of times to clean this up.
Very good. So show us how it gets a little bit cleaner if you take the logs of the likelihood first.
I mean, it was still, but sure, it got cleaner.
Well, at least it didn't have any display style. Like it's so hard. It's so much annoying stuff. You can't even see that it didn't display right.
Okay. Yeah. So for this problem, we're like everybody else said, we're looking for the value of theta that maximizes this probability. But if you use log differentiation, what you can do is, because the log of a over b is log of a plus log of b, you can use that to break this up into 2 log terms and then use the chain rule. So here I let y of theta be equal to gh to the k. I made it into one fraction, and then I let it be equal, I took the log of the whole thing, basically. And so this is what you get when you take the logarithm, the exponent pops out. And then I did the derivative of both sides. When you do the derivative of like log of theta, you do the chain rule. So you get one over log of, or y of theta, which I think is just log of theta here, and then the derivative in the top. And the reason that I did this was because you're trying to let y prime of theta be equal to 0. So I got it into this format, and then I solved.
Stop right there. When you have 0 equals something, that first term has a theta term, which is positive, 1 plus theta, which is positive, k, which is positive, a 1, which is positive. That first bit there is certainly not 0, nor is it negative.
Oops.
So I can scratch that little guy out right away. And now I have k over theta minus 1 plus k over theta over, k plus 1 over 1 plus theta is equal to 0. Pop that to the other side, and I have k plus 1, 1 over theta plus 1 equals k over theta.
I felt a little spooked about just eliminating like an entire term immediately. So I tried to justify it to myself by slowly eliminating the denominator. But yes, I could have just thrown it away.
Throw it away. The 0 on this is absolutely a positive number. It's just in your way. And from here, whether or not you continue the algebra, almost everyone rational will see if k over theta minus k plus 1 over theta plus 1 is 0, k equals theta.
I'm a little formal, sorry.
No, that's very good. That's very good. That's doing it formally has never hurt anyone ever. But the reason it is often easier to do things in log space is because, well, the derivative of a log is just like 1 over that little mess there, which is sometimes a little bit easier to handle. And it is not infrequent when you do this in log space, you can get a whole term, a whole mess of terms drop out pretty quick. And the reason you're doing it in log space is to look for that trick, is to look for this mess of positive things that I can just scratch away. And in fact, for the statistical adults, I tend to think of a likelihood as not a probability, but as something sort of linearly proportional to a probability, because most of the time they have divided away constants or subtracted them off in some fashion. So the likelihood they're working with isn't the actual probability, but is something more like this interior term of k over theta, something like that.
Yeah, it doesn't look easier in my version because this y of theta could have just been gotten rid of immediately, and then it would look easier.
And it would have looked much easier. Yep. Anyone else want to talk about this problem? So we've gotten to the holy, sort of trinity here of two sequences. So what we found is the probability that there were k differences between them was equal to equilibrium homozygosity times heterozygosity raised to the k. That and the only parameter in those things is theta. We then found the expected number of differences between two sequences was theta. The variance between them was theta squared plus theta. And if you observe k differences between two sequences, what is your best estimate? What is the best possible estimate of theta you can make? K. This is it for two sequences. There's almost like this deep one-to-one correspondence between the observed number of sequence differences k and your ability to estimate theta, which is the best you're ever going to do. Just set it equal to the observed number. And sort of says when we're looking at two sequences, there's almost nothing to see there other than theta. And in fact, really, when looking at any number of sequences, there's nothing to see there other than theta. Almost everything about the distribution is knowable as a function of theta until we get recombination.
How are we defining sequences in this context then? Because, you know, K sites in two sequences, is it chromosomes? Is it?
Sure, it's anything you like. It's anything you like, but there is no recombination. So you have a very, very intuitive notion that there is always recombination at a chromosome level for every meiosis. So this is a shitty approximation at a chromosome level. At a 3 nucleotide bin, you think that's that's tiny little centimorgans of tiny centimorgan, and maybe a 1/10 of my sixth of a centimorgan, just a little bitty bit. There's no recombination for that range, effectively, at least for many, many, many generations. So for tiny little bits, you think this is probably a great approximation. Maybe even to the exon level, it's an okay approximation. Once you start thinking about whole genes, maybe you start thinking there's significant recombination. And certainly at chromosomes, you know for a fact there's a lot of recombination at the chromosome level. So this is clearly going to be a good approximation when looking at very close to an individual nucleotide level, and it's going to be a very poor approximation over scales the size over which you might expect recombination. And that word recombination hasn't been defined in this class yet. I promise you it will be, but it may not be defined until homework 6 or 7 or something. But we shall talk about recombination, and we shall talk about sort of the scales over which recombination works, hopefully. And we'll get a sense for why this no recombination approximation is very good over tens or even thousands of bases, and very poor over tens of thousands or millions of bases, hundreds of thousands or millions of bases. But we'll get a better sense of that once we get through many other homeworks. Other questions? Okay, I think we're going to start doing some applications. Is Carmen around with problem 14? She had to step out.
Yes. Okay. So I forgot what the problem was. Sorry, I have to look it up again. Okay, so this is the expected mutation.
Yep.
And I used the equation that was in the book of TC times mu equals expected mutation. And then I just used the expectation of TC and solved for that.
So this little bit in here, this looks like the sum of like 1 over I from I equals 1 to how many alleles were there here?
I used 20.
Let's see, I'm going to peek at my solution. What did I? Yeah. So let me show my version of this, which is, I think it's very close to, let me show my screen just to, so I said the expected number of sites was equal to theta per site times the expected, times the length of the region, times this it was apparently there's 100 sequences here.
Okay.
Yeah.
There you go.
There are 100 sequences here. So yeah, 100 chromosomes. So this sum term here looks like the sum from, not 0, the sum from I equals 1 to 99, not 0. That's a very ugly thing to put down there. So it's the sum from I equals 1 to 99 of 1 over I times theta times the length. And the theta given was 10 to the minus third. The length was 20,000. So for the entire region, theta is 20, and that sum is something like 5.18. And that's that. Does this make sense to everyone? So this sum, the sum from I equals 1 to 99, 1 to n minus 1 of 1 over I is, again, I put the zeros, is very, very close to the natural log of n. It's really sort of shockingly close. It's even more shockingly close to the log of n plus a constant that's equal to about 5.77. So this sum for large n, any sort of moderate n, you should think in your head about as a natural log. So the sum of 1 over I from I equals 1 to 99 is very close to simply the natural log of 99. It's even closer to the natural log of 99 plus a half. So the expected number of sites for no matter, so we now start sequencing, you're now going to do a large experiment. We're going to sequence hundreds of people, thousands of people. You know, if I sequence 2 people, the expected number of sites is theta, or theta per site times the length. If I sequence 1,000 people, the expected number of sites is the natural log of 1,000 times theta. If it's 1,000,000 alleles, it's the natural log of 1,000,000 times theta. And so the natural log, right, is a number between like 2 and 3, right? It's 2.718, whatever it is. It's something like that. So you can do, most of us can do powers of 2 in our head. You know, 2, 4, 6, 8, 10, or 16, 32, 64, and so forth. Most of us can actually tell you that like the natural log of 2 to the 10th is about 1,000. 2 to the 20th is about 20. I mean, it's 1,000,000. 2 to the 20th is 1,000,000. 2 to the 30th is about 1,000,000,000. So the natural log of a number like 1,000, it's going to be a little less than 10. It's going to be, you know, it's going to be smaller than 10. The natural log of a number like 1,000,000 is going to be less than 20. Natural log of a number like 1,000,000,000 is going to be less than 30. So if you sequence one person, you're going to get some number of sites. You sequence 1,000 people more than that, 1,000 times more than that, you're going to get less than 10 times more sites. If you sequence 1,000,000 times more than that, you're going to get no more than 20 times that number of sites. You sequence 1,000,000,000 times more than that, you get more than 30 times that site, because that sum scales like a natural log. In a natural log, you know, 2.7 to the 10 is definitely less than 2 to the 10. But that should be your intuition whenever you see a sequencing experiment from now on. That if you think you know the per site theta, and you think per site theta is on the order of 10 to the minus third, because it is, certainly if it's human, but often in your favorite organism, that's true too. But if it's on the order of 10 to the minus third, you think of how much sequencing did they do? Okay, they did 20 KB. All right, I expected about 20 sites if it were 2 sequences. How many did they do? They did 100. Okay, I expect maybe 5 times that. So if they walk in and show you data from 18,000 segregating sites in their sample of 100 people, you immediately say you've got a data quality problem. That something is deeply wrong with your sequencing. I expected 100 sites, not 5,000. And um, you will find over the course of your career that the actual number of segregating sites you see is not dramatically different than the neutral expectation effort. Almost never is it deeply, fundamentally orders of magnitude different than the neutral expectation. If it's orders of magnitude different than the neutral expectation, almost surely something went weird on you. And it wasn't the biology. It was something technical.
Sorry, can I ask a question before we move on?
You bet.
Well, I'm just curious about this you mentioned. I don't know, like why it's like from I equals 0 until n-1 and not like 2n. I didn't get that bit. So my answer was like off by 1. It was 104 for me.
Yeah. So the answer comes from this picture. So the time, so if you have, say, 1, 2, we got like 10 sequences here. The expected time till the first 2 sequences coalesce looks like 1/2n generations, because every time we were doing our picking, we're picking one person from the previous generation and asking whether these 2 people from this generation had the same mother last generation. So the probability of that is 1/2n. So we expect the time to look like scale as 1/2n, but the number of different pairs of sequences that might have shared a common ancestor last generation, where if I have 10 sequences here, it's the number of ways I can pick 2 people out of 10. So that's 10 choose 2, which is equal to n times n-1. So the time to the common ancestor looks like 10 times 9 over 2n for the time until this event. But when that event happened, I've had evolution going on in this lineage, in that lineage, in this lineage, in this lineage, in this lineage, this lineage. I've had evolution going on in 10 different lineages. So the total amount of time in the tree looks like n times n-1 over 2n, or 2n, rather, I said it's backwards, 2n over n choose 2 over n times n-1. But the total number of sequences over which that could evolve is n. And I've got an n on the bottom and an n, they cancel, and I get the total time in the tree is equal to 2n over n-1 to the first event. To the second event, it looks like 2n over n-2. To the next event, it looks like 2n over n-3. The total time here looks like 2n over n-4, up to the last set of events, which looks like the total time looks like 2n over 1. And the proper derivation is in Gillespie's book, if you'd like to see it. But the intuition is the number of ways I can pick 2 individuals to coalesce looks like n times n-1. And the total number of lineages that are evolving looks like n. Those n's cancel, and you end up with an n-1 on the bottom rather than an n. But if you don't believe me, the only thing that's going to happen is you're going to have to do the derivation sort of properly. And as a result, the expected number of mutations in the tree from the last coalescent event is equal to theta over 1. The number of mutations between the second to last and last coalescent event is equal to theta over 2. The number of mutations you expect in the next tranche is equal to theta over 3, and then theta over 4, and then theta over 5, all the way working your way down the tree. So to say that again with that picture, I'm an idiot. Come on. So the total number, the expected number of events in this portion of the tree is theta over 1. In this portion of the tree, it's theta over 2. In this portion of the tree, it's theta over 3, and so forth, until you get to theta over n minus 1. That was sort of Jeff's original derivation. Other questions?
Sorry, just kind of asking for a little bit of a repeat of what you were saying regarding dealing with sequencing data.
Yeah.
Is that, is assuming we have a pretty good approximation of theta for humans, I guess?
So in fact, this is a really good estimate of theta for all of humans. If your humans were only like pasty white people from Northern Europe, your estimate of theta might be closer to 80% of that, might be 8 times 10 to the minus 4th. But if you have a broad collection of humans from all over the globe, there's 10 to the minus 3rd is a really good estimator of theta in humans. It will be less than that if you've restricted yourself to only people from a single continent, so that there's just less there is less variation among people whose ancestors are only from Europe than there are in the globe overall. Other questions? Okay, I will stop my share. And hey, Jim, you're actually up next with the next problem.
All right, or is it 15?
15, it looks like.
Yeah, okay. So I don't think I did it the right way, but we can see. So the question was saying you have a 20 kb region, 10 diploid individuals. You find that 19,900 of those bases, there's no variation. Estimate the theta for the entire region and then divide it by 27,000. So I didn't quite get to the end part because I've just fixed this after what you were telling us a second ago. But so I tried to use this formula from the book, which is saying theta is equal to number of segregating sites over this mess.
Yeah.
I didn't know how to figure out what the mess on the bottom was until just now, when you approximate it as a natural log, I guess.
Yeah.
So
the mess on the bottom is a little bit more because it's 10 diploid individuals, and presumably you've sequenced both alleles. So it is maybe even 20 alleles total.
okay, so it's really going up to n equal 20.
Yeah.
In this case, because of diploid. Got it.
But
Okay.
so if I make that the natural log of 19, but now let's talk about the top number. SN is simply the number of sites you found.
I think I did that differently. I tried to divide it.
Yeah. Oh, you were trying to get to per site right away. I see. So
no, not on purpose, but maybe I did that accidentally.
Yeah. So maybe you were saying, okay, screw this. I'm just going to go on a per site basis. And the number of segregating sites, it's probably more straightforward. Let me.
Should it just be 100 then?
Yeah. Let me just show you what I got. Let's walk through the way I've done it. I haven't shared my screen, have I? Let's try again. Share screen. Homework 4. So 20,000 sites total. That means 100 of them are segregating sites. So S is equal to 100. Now it's just plug and chug. So the expected number of sites is equal to theta times the sum from I equals 1, not 0, the sum from I equal 1 to the number of alleles minus 1. If there are 20 alleles, if there are 10 people, 20 alleles, so the sum from 1 to 19 of 1 over I. That's the expected value for the number of sites. So a good estimator of theta might be the observed number of sites divided by this thing, because the expected number, theta gives rise to the expectation. So you can sort of think of this as a first moment estimator of theta. It's one where we have equated the parameter to the expectation, and we plugged in for the expectation the observed number. So here the observed number is 100, and we're going to plug that in and pretend that was the expected and find what value of theta would have given us that. So it's 100 divided by that sum, and that sum turns out to equal 3.5. That's equal to all right, everything beyond that's arithmetic. So the words from the problem, we have the length of the region, 20 kb, 10 diploid individuals, which means 20 alleles were sequenced, which means the sum runs from 1 to 19. The number of segregating sites were reported to you in a weird way, but it was 100. And everything else is now just a little bit of arithmetic to get us theta for the entire region is 28. And it said the region was 20 kb, which got us to that number. And this is a bread and butter problem. Expect to see stuff like this the rest of your life, and therefore expect to see stuff like this on the exam, because we're going to try to practice and make sure we can get from the number of sites we see to an estimate of theta, and vice versa for our own sequencing experiments, so that, that we know both ahead of time, because we thought we knew theta, what we should get out of our sequencing experiment. And then if we observe some number of sites, we can back calculate and figure out what theta probably is, or at least an estimate of it is, and see if they're in any way compatible with one another. It'll be one of our useful sort of data sanity checks the rest of our life. So expect little problems like this on exams. And the only tricky part is like just getting the words right. 20 kb region, okay, that's the length of the region. How many people did we sequence? Well, if they're diploid, it's probably twice that number. Make sure you subtract the ones, that kind of stuff. That's where everybody is going to, like lose a point here, lose a point there.
So is a segregating site then just basically a place where there's variation?
Yes. So that is a population geneticist's term for a site where you see more than one allele in your experiment. So God Almighty, that's an ancient word for it. But segregating here means that something is observable that obeys Mendelian laws in the experiment I'm doing. So that when it is a heterozygote, it gets transmitted to offspring, half the time. So something that is segregating means it has variation I can track in a pedigree, literally. And in a sequencing experiment, a segregating site means that it is a site with more than one allele that I presume, were I to put it in a pedigree, it would obey Mendel's laws, because everything does nowadays. But the term goes back to when the question was, are Mendel laws correct? It's ancient. And, but it's what all of us old people will use to describe a site of variation that we sequenced. Yes, that term is the opposite of intuitive until you get to a certain age, and then you forget how stupid sounding it is. Does that make sense? Okay. Up next is Mega with problem 16, I think.
Let me just share. Okay. So for 16, all I did was I multiplied. They said that there was 0 heterozygosities at the 19,900 other sites. And so at the remaining 100 sites, there was 0.2, and I divided it by all of the base sites to get our H hat. And then I set that equal to the theta equation and solved for theta and got 0.001.
That looks awfully good to me. Anybody do anything different? That the problem? Yep. Absolutely. So in the last two problems, we have estimated theta from the number of segregating sites and gotten the number 1.4 times 10 to the minus third. And then we've estimated theta from heterozygosity and gotten the number 1 times 10 to the minus third. There is so I'll share this just a little bit because although that is exactly what I wanted you to do, I'll also point out that so I've done it exactly the same way. I said at 100 sites 2PQ was equal to that. So their sum was 20 over a whole lot of sites. 2PQ was 0, and therefore over all 20,000 sites 2PQ is 20. Therefore my estimate of heterozygosity per site is equal to 20 over 20,000, or 10 to the minus third. It turns out Gillespie tells us on page 45 of my version of the book, which is above problem 2.13, that this estimate of theta based on heterozygosity per site is very slightly biased. And the bias is in terms of your sample. So if you've sampled N chromosomes, this estimate of theta turns out to be an underestimate, a biased underestimate by a factor of N over N minus 1. And a slightly better estimate of theta would have been to take that number 20 and multiply it by 20 over 19 and have gotten the number 21 rather than 20, and plug 21 into this. Doesn't make much difference. 5% or something. So you will see other people's, like when you use Tajima's formula for the estimate of theta, you will see this term N over N minus 1 in it. And it is nothing more than just adjusting heterozygosity because your estimate of the variance is biased by N over N minus 1. We can prove that, but let's just accept it for now. But you can sort of see for any reasonable values of N, there's even 20, there's hardly any difference between the simple-minded sum of 2PQ and the less simple-minded sum of 2PQ over times N over N minus 1. And up next, as we start getting into the can you do arithmetic side is Taylor. Can you do arithmetic, Taylor?
I did it wrong, so yeah.
Did you? Okay, let's see if we can guess where it went wrong.
So again, I'm lazy and don't like doing arithmetic, so I just wrote an R function to calculate this D statistic. So basically you take the two estimates derived, I think it was 16 and 15, pi hat is your, so I have pi hat here as my per site estimate, and I think
Yep.
it should be per locus. So I'm on the wrong scale here.
Yep.
So I think that's where I went wrong. And then theta hat is our estimate using the number of segregating sites. So these are on the wrong scale, but this is just a whole bunch of algebra. And here's my estimate, which is incorrect. So.
Yeah. So okay. So let's talk through this to get to the right answer. So Tajima's D is supposed to be a test to ask whether when I estimate theta two different ways, are they the same or are they different? So pi hat is my estimate of theta from heterozygosity. Theta hat is my estimate of theta from the number of segregating sites. And Tajima had in mind the idea of trying to make a statistical test by trying to make this thing look like a Z statistic. So what he has is the same parameter estimated twice, which has expectation 0. And what he wants to do is try to divide that by his estimate, by an estimate of the standard deviation of this difference, or the square root of the variance of this difference. So he is going to take theta, estimated twice, which ought to have expectation 0, and divide it by an estimate of that standard deviation, which now makes this thing look like a z-score, roughly. And we're going to test this as if it were a z-score, maybe, or maybe we'll do something slightly different. But mostly in our mind, we're going to test it like a z-score and ask whether it's statistically different from 0. So if it's a number like -2, it's probably P05 different from 0, with the estimate of theta from segregating sites being bigger than the estimate of estimate of theta from heterozygosity, meaning there were more segregating sites than there was heterozygosity. If this number looks like a number like -2, it looks like a number like +2, it's probably significant at 0.5 the other way around. If this is a z-score, and it's kind of close. But in any case, this term on the bottom, this denominator, is supposed to be an estimate of the variance in that difference, and it is. So just because I might have done it right, let's sort of plug in some of the numbers I had. So again, I've written Tajima's D as an estimate of theta from heterozygosity minus an estimate of theta from segregating sites, divided by really sort of what I hope to be the variance in that difference. We will not derive this. It's a painful sort of Taylor expansion approximation, but Tajima asserts, and in fact he is correct, that a decent estimate of the variance in this difference is this piece of garbage here, which has both the number of segregating sites in it and a whole bunch of constants. The scale, as Taylor said, needs to be in per region. Otherwise, everything's going to look like, it's going to look like you've just divided your z-score by the length of your region, or something like that. So the score has to be, the statistic has to be in terms of region length. So you're going to have an estimate of theta per region, which was like 21, theta per region, which was like 28. And then everything else here is number of segregating sites observed, whatever that happened to be. I think it was 100 here. And then these sort of ugly looking functions of A1, A2, B1, B2. I combined some of them here. Some of those A's and B's I just called C's. But the A1, this actually occurs a lot. This notation for A1 for the sum is not uncommon. This notation of A2 for the squared sum is not uncommon. So I left that the way it was. But for some of the others, I collapsed terms. And the little n you see is number of alleles. It's just plug and chug. And if I have done the arithmetic correct, the answer was -1. And is there a chance I have done the arithmetic wrong? Oh yeah. Oh yeah. But I think it is correct. And it is nothing more than plugging those things in. But intuitively, you all should have the idea that Tajima's D is a test of neutrality, because I know when all that's going on is mutation and drift, that this thing is an estimate of theta, this thing is an estimate of theta. They ought to agree with one another, so their difference ought to be 0. And therefore, if I take the observed difference and divide it by the variance in that under the neutral model, this thing ought to resemble a Z statistic, so that numbers bigger than -2 or 3 are really sort of significantly tiny. Numbers bigger than +2 or 3 are significantly big. And we ought to be surprised when we see them, or at least a little surprised, under at least a constant size neutral model. Does this make sense to everybody? So this is one of the first tests that asked whether your observed frequency spectrum was consistent with sort of constant size neutral population estimation. And it did it by estimating theta twice, because in a constant size neutral population, theta is the whole world. So if you estimate theta one way, you estimate theta another way, you ought to get the same answer both times. Clear to everybody? This, everyone manages to screw up plugging in the numbers. You have to make a formula. You have to do it in R and have to do it like really cleanly and to get it right, because it's nothing but nuisance.
Actually, can I ask? I just want to clarify how you were able to compute pi hat.
How I was able to compute pi hat? I did it in the previous problem. So
okay.
Yeah, I just pulled it from the previous problem.
Because
is that right?
On Wiki,
or did was
no,
this,
I was.
Yeah, I think I wanted to just use it from the previous problem.
Okay,
So,
because on Wikipedia it was using the total number of pairwise differences normalized by n choose 2.
Oh, that's right. So that's right. It doesn't the total number pairwise differences.
So I can share what I found, because I think the numbers are slightly off. Actually, they're off quite a bit, so I'm not sure.
No, they're not. They're exactly the same. It's provably the same.
Okay, so this is 17 and let me see how I computed. So pi here. So I know that I have 100 segregating sites. So on average, at each site, 4 out of the 20 sequences, because we have 10 people, 10 diploids, so that's 20 sequences. So on average, 4 out of the 20 sequences at each site, they're different from the reference. And so in total, there will be 16 times 4 pairwise differences at each of the 100 sites. So I should have a total of 100 times 16 times 4 pairwise differences. And then I'm normalizing over 20 choose 2. That's the Wikipedia formula. And this number is around 34. So that's
totally not right. So wait a minute, maybe it should give you it. So wherever we used heterozygosity, so you've used heterozygosity at saying, so this is going to be easier if you do it the other way around. If you start with 100 sites and make the frequency of one allele P the frequency of the other allele Q, and make 2pq equal to 0.2. And from there, derive the average number of pairwise differences. You will find it is 2pq. Like the reason, so when Tajima derived, let me see if I can even find it. Tajima derived his heterozygosity pi measure. He did it. So can I share this with you guys? So, share screen, yeah. Google, yeah. So when he derived his original pi estimate, he did it in terms of counting the number of nucleotide differences between every pair of sequences, and then taking the average number of differences between each pair of sequences. He called that k hat, and from k hat, he found an estimate of theta. If you think about it, you don't even have to think about it very hard. You can very rapidly show that this thing looks like the sum 2pq over every site. And therefore, Gillespie doesn't bother to present this horrifying pairwise thing that you can't calculate in any sort of, in anything other than like forever by picking pairs of samples. He gives you the formula where you just calculate it by taking 2pq. And that the number of pairwise differences, the average pairwise differences, looks very much like 2pq will become intuitive to you after a minute when you try to establish it. And so when Gillespie presents it, he doesn't ever present it with this uglyish formula when you can just do it from pairwise heterozygosity. So there's a proof in there that we didn't show you, but trust me, it's an identity. Pairwise differences, the n over n minus. In fact, the pairwise differences will give you the variance normalizing term with n over n minus 1 in there. It will give you the exactly correct formula, the unbiased formula that Gillespie presents. But we'll leave that as an exercise for home. Trust me on it. And never, ever, ever go back to pairwise differences. It's such a pain to calculate from real sequences. Whereas, it's a quadratic calculation rather than a linear one, under the assumption that you need to know the allele frequency already anyway, that you've probably calculated it already. Any other questions on this? Michelle around? No, she is still recovering from her qualifying exam. Linnea, you were up next.
All right. Let me share my screen. Oops. What am I doing? Okay, there we go. All right. So 18? Yes.
Yeah.
Okay, so all right, so this is just estimating for a nu for the silent variation at each locus. Okay, so the setup to this problem was, I think, you're allowed to estimate this on the silent variation, but not the actual non-synonymous, because those are not necessarily neutral, if I remember that correctly. Is that the case?
We're in a world where everything is neutral. Don't you? There's no such thing as non-neutral yet. At least until we
Okay,
do
okay.
one more chapter and learn what it means not to be neutral. There's no such thing as non-neutrality at the moment,
All right.
even though we just constructed
Well,
the test. But that test is never significant. So there. Okay.
okay. So I think there was only 13 segregating sites that were silent, and the other one I think was not. So we just basically, I think I just redid exactly what they did in the book, but just changing SN to 13 instead of 14.
Yeah,
I believe, and then yes. So basically, you get this 4.43 for the entire locus, and then there was 768 sites, I believe. So that's the per site value.
So let me peek. So you got 4.4. Yeah, that's it. Okay, done. The right thing to say might be for the region you got the number. So let me looking at your answer. So for the region you got the value of theta of 4.4. That is 100% fabulous, no question about it, correct. On a per site basis, most people report per site thetas in terms of number of sites that could have been that thing. And you don't know that for silent sites here. The entire region is about like 700 bases, but the number of sites that are capable of mutating to a silent site is not obvious. It's probably a third of that or something. So, so I didn't even anticipate you trying to put this on a per site basis, but if the entire region were silent, for sure that's correct. But if not every site is capable of mutating to a silent site, your estimate of the number of sites is probably going to be smaller than that, and probably closer to a third that number than the number itself.
Okay.
But absolutely, that's just 100% correct. 4.4 for the entire locus.
Cool.
Next question. You didn't tell me.
Right.
Okay, that's it. We're done. Does this make sense to everybody? That, in fact, looking at a sequence and telling you how many sites could have been silent and could have been replacement or capable of changing or could have been a stop codon is almost not possible other than by walking through the sequence and changing it at every spot and asking, what does it make? And so when people start reporting things per site, they've probably, honest to God, either suggested a dumb approximation or they went through and counted up how many different mutations would make a silent site, how many different mutations would make a replacement site, how many would make a stop codon, and counted that up. And there's no other easy way to do it, really. All sensible? Brooke, with the next question. Problem 19.
Okie dokie. All right, I will share my screen. And I know too that my scales are going to be a little bit off because I was using
Per sites?
Yeah. But also I'm not entirely sure I had exactly the logics, but we shall see, I suppose. Okie dokie.
All right, this is.
Just make this bigger real quick for myself. Okay, we are at 19.
Maximum, minimum of Tajima's D. This is
Yep. So I also used an R code that just was the, my calculator for C value.
Yeah.
But basically what I was thinking about it, how I was thinking about it is for the minimum and maximum values, I was thinking about what that would do to minimize and maximize heterozygosity. So that would be if you're, so for your minimum value in a neutral population, you might I think you would have to have your population be 1 or G equals 1 minus H. And then basically sub in H with 1.
So,
and
so this is getting there, but the problem has told us there are 10 alleles and there are 20 segregating sites. So the minimum heterozygosity, this is minimum we're going for here, right?
yeah,
So the minimum heterozygosity at any site is probably P equals 1 over 10 at these 20 sites. And the minimum at all the rest is 0. Does this make sense? So let me share my screen.
Can I ask a question?
Yeah.
So wasn't technically, couldn't you discover no, like even if they're segregating sites, couldn't you still discover heterozygosity could be 0 there just because you observe it that way?
No, because the word here segregating means I have observed variation.
Okay.
That is the so at 20 sites. So to read this, and now using the peculiar notation, peculiar words of a population geneticist, I sequenced 10,000 bases in 10 alleles, and I found at 20 of those 10,000 bases, there were 2 nucleotides among my 10 alleles. That means that's what segregation means here. In these 10 alleles, at 20 positions, there were 2 different nucleotides. So those parameters there circumscribe the problem. 20 segregating sites, 10 KB, 10 alleles. So that I already have enough information to calculate theta for the region using Watterson's method. 20 segregating sites, 10 alleles, sum from I equals 1 to 9 of 1 over I. That gives 2.89. That gives a number of about 7. So given that it is 10 alleles and 20 segregating sites, for the entire region, for sure my estimate of theta from Watterson's method is going to be 7.7. And also, the denominator of Tajima's D is already determined. That estimate of the variance there is a function only of segregating sites and sample size n. If I did all my little bitty arithmetic correct, I would find the denominator is equal to 1.5. I might have gotten my arithmetic wrong. If so, I'm sorry. But the denominator here is 1.5 if I'm correct. So the problem comes down to asking what is the largest, as Brooke points out, what is the largest value of pi hat and what is the smallest value of pi hat? So if you guys, so again, I'm going to use the definition of pi hat that involves P's and Q's because I can do math on that much better. And you all will remember from like week 1 or 2, the value of P that maximizes heterozygosity is 1/2. So if I'm trying to maximize heterozygosity, I'm going to assume all 20 of these sites has frequency 1/2. So 2PQ is 1/2 over all of these, it's 2 times 1/2 times 1/2. It's 1/2 times all these sites. I've got the sum of 20 of them. So I have 10 over 9, my unbiasing factor, times the number of sites, 20, times a heterozygosity of 1/2 at all of those sites. That gives me a value of about 11 for pi hat. And therefore, a maximum value of Tajima's D, well, I'll just plug in the 11 and get something, 2.7. To find the minimum, it is the exact same logic, but I know because it's segregating that at least one of my 10 alleles had to be one of my two things. So in order to make heterozygosity minimum, I'm going to make one of them equal to 0.1 and the other equal to 0.9. You remember the sort of graph of heterozygosity looked like a parabola. So the closer you get to 0 or 1, the lower heterozygosity is going to be. So I'll make p equal to 0.1 and q equal to 0.9 or vice versa. It doesn't really matter. And my minimum estimate of pi looks like, again, this is 0.1 times 0.9, that's something. At times 2, we get 0.18, 20 sites, 10 over 9. Apparently that's the number 4. Okay, so the minimum to G minus D is equal to 4 minus 7 over 1.5, which is minus 2. The maximum was 11 minus 7 over 1.5, which was 2.7. And that's pretty typical of any sequencing experiment you're going to do. G minus D is almost always in the range of -3 to 3. And for small samples, it's often bounded in the -2 to 2 range.
So just a clarifier to rephrase. So for minimum values, we're really not, like, we wouldn't, if we know that we're observing any kind of variation, the minimum is not going to be 0, but it's instead going to be basically what it could possibly be, which is that
minimum times you can see
kind of our, like, all of our alleles that we, hold on, what was it at 10 again?
10 alleles.
5 diploid, okay, yeah, 5 diploid individuals, 10. So that those 5 sites would be, okay.
If it's segregating, at least one of your 10 alleles is one allele, and the others are the rest.
Okay.
Maybe it's 5 and 5, or 4 and 6, 3 and 7, 2 and 8, 1 and 9. Those are the limits. So when it's 1 and 9, heterozygosity is going to be minimum. When it's at 5 and 5, heterozygosity is going to be maximum. And you're kind of already probably seeing how you can get to pairwise differences to PQ. This is going to start falling out in your mind pretty soon. But there you go. So the G minus D is probably a pretty weak estimate, a pretty weak test of neutrality. Maybe the strongest test there is, but you're not going to get values out of it if you test this against a z-score that is significant at 10 to the -4th. It's like almost impossible. If you approximate the distribution with a z-score, or you approximate it as Tajima suggested with a weird beta distribution. Either way, you're still not going to get results that would cause you to call this incredibly significant under the null model, no matter what data you see. But at 2.6, you'd probably reject neutrality, and at -2, you'd probably reject neutrality, at least weakly at 0.05. Or perhaps I should say constant population size neutrality. But in this case, every single individual is like, every single allele has frequency 50%, and you get a G minus D of 2 point something. Here, every single allele is a singleton, seen only once in your data, and you get a number like -2. And you should expect that. If you get a number like -2 or worse, probably most of your data was singletons. If you get a number like +2, most of your alleles were incredibly common. Questions? And lastly, we have Sebastian with the last problem of the day. Problem 20, the molecular evolution one.
I'm muted, sorry.
No worries.
I was just fixing my code for like
Yeah,
15 through 18.
Yeah.
So
Okay, that's good to start with. Excellent. So tell me what those numbers are.
just give me a second. I need to find the book.
Yeah.
I forgot to write down the equation. So for for this, I use the equation that's on page 32, which is rho equals to the nucleotides they differ, and I divided it by this factor given by the generation, the time to get a new generation for humans.
And what would I call that number right here? The number that you've written up at the top that has 0.00002. What is that an estimate of?
It's an estimate of the rate of substitution.
Per what over what over what?
Over a million years, I guess.
Yeah, but I mean, there is a component here of you've estimated the amount of evolution over a single site, over the whole region, over.
This is over. This is for the whole region. So beneath this is beneath is per site.
Absolutely. So what you said is there are 200 bases difference. Those differences occurred over 10 million years. So I get a rate of evolution for the region of whatever that is. And then I divided that by the size of the region to get something.
The substitution rate, yeah, per nucleotide. And then I use that substitution rate for, oh my God, whenever I don't write down the equations in the homework, I just forget what I did.
No, this is fabulous.
So this is basically theta equals to.
So let's slow down and stop at your second equation. So you have rho here equals what looks like 10 to the minus 9th. I'm going to say that's 10 to the minus 9th if I can count zeros correctly. And so rho here for neutral evolution is an estimate of the mutation rate. So what we've calculated here is if there are 200 differences divided by the amount of time here is measured in years. So we got an estimate of the rate of evolution as the number of differences, 200, divided by the total time. That's for the whole region. And we got this thing that looks like 1, 2, 3, 4, 5, maybe 2 times 10 to the minus 5th per region is our estimate of the evolution rate per year. Then we took our estimate of the evolution rate per region per year, divided it by the total sequence length, and now have an estimate of the rate of evolution per site per year, and came up with 10 to the minus 9th per site per year. And so this is the rate of evolution, which under the neutral model is also the rate of mutation. So right here, this line of rho equals says our estimate of the mutation rate per site per year is 10 to the minus 9th. And the rest of the problem said, suppose you knew what theta was in humans, and you've used something like this as an estimate of theta in humans, 9.6 times 10 to the minus 4th. It's a pretty good estimate right there. And this thing's a little confused at the end. This 5 million thing is a little weird. It shouldn't be there. But what you've said is if theta is 9.6 times 10 to the minus 4th, and population size and mutation rate is 10 to the minus 9th is 10 to the minus 9th this is the value per site per year, you would then estimate 4n as this number, 10 to the minus third-ish, divided by this number, 10 to the minus, and gotten something, probably that might be right. I don't know what that 5 million is, but that might be correct. No.
I don't know where I got it from.
A
I'm
little
still
off.
trying to figure that out.
But I will show you my screen. We're very close here for a little bit, and let me show you where I am with this. So we start out like being very, very similar. Only I probably divided into a per site right away and started with 200 over and made that number 0.1, where you left it as 200, then divided by the number of sites a little bit later. But in any case, we have some measure of the amount of evolution is the mutation rate per year here, because time is on a scale of per year. That's the amount of time. And we got an estimate of the mutation rate per year as 10 to the minus 9th. Now, for me in problem 15, my estimate of theta was 1.4 times 10 to the minus third. You had 9 times 0.6 times 10 to the minus fourth. They're off a little bit, but we're not going to worry about that little difference. But the big thing to say here is theta, the mutation rate for everything we've done so far, has been per generation. Nothing we've ever done in this class, nothing we ever will do in this class is the mutation rate on a per year basis. It's always on a per generation basis. So this estimate of theta of 10 to 1.4 times 10 to the minus fourth uses a mutation rate per generation. But this evolution calculation, I gave you the time measured in years, not generations. So if I'm going to convert a mutation rate measured per year to an estimate of the mutation rate per generation, I probably need to know what the generation time is in humans and chimps and in their ancestor. I didn't tell you that in the problem. And so any reasonable guess of the generation time is probably reasonable. I kind of think humans have a generation time of maybe around 20 years. I kind of think chimps might have a generation time around 5 years. So I don't know. I'll guess the average generation time is 10 years, maybe. I don't know. Maybe not. You know, maybe that's sort of reasonable. If you'd said the generation time is 5 years, I think it's probably reasonable. Said the generation time is 20 years, that's probably reasonable too. Generation time of 1 year is probably not reasonable for a big primate. So we know the per generation mutation rate is probably bigger than this, but maybe it's 10 times bigger, maybe it's 20 times bigger, something on that order. So I'm going to use my estimate of the per generation mutation rate to be 10 to the minus 9th times 10. This is a convenient number, giving me 10 to the minus 8th. And then we did it exactly the same way. Theta equals 4n mu per generation. I have a little bit bigger value of theta than you did, but that's still 4n times 10 to the minus 8th. I then divide and I get n is equal to 35,000-ish. Does this make sense to everybody?
I think the value for theta I had was like really wrong, because like instead of having n in my formulas, I was using the number of nucleotides. So that's the difference. So now that I changed that, I get the same value, but I didn't have time to change number 20.
Yeah, no, that's great. Exactly. That's perfectly fine. The thing is to understand, for whatever value of theta you had, this was the right calculation. This was the calculation you did. And that's all one can ask. The only real difference was I made the scale change from year to generation, which is sort of really necessary. Does this make sense to everybody? So the fact that we tend to observe molecular evolution on a scale of years, because we sort of often know like how old fossils are in terms of years rather than generations. But all the theory says mutation rate per generation is really what is going to matter for these calculations. it will lead to some oddities in the molecular evolutionary record that we'll sort of probably talk about a little bit in the next chapter. That some things seem to be evolving constantly on a per year basis, not per generation basis. And that's just kind of wrong under the neutral theory.
Isn't that like problematic when studying evolution of life history traits?
Yep, you bet. When studying like the evolution of almost anything, certainly of proteins and anything else, we'll talk about a lot next chapter, hopefully. But this is to warm us up that it's to remind us that everything we've done in this class up until this moment, if it had the word mutation in it, it was on a per generation basis. But if someone observes something, it might have been on a scale of years, and you might have to deal with the fact that a generation isn't a year unless you're in a plant or something that's often like where a generation is beautifully exactly a year. But for big mammals, a generation is almost always more than a year. For little flies, it's almost always less than a year, maybe. And for maybe mice, it's somewhere in between there. Let's start thinking about these things. Is there any question about this homework?
I was just kind of wondering what this last problem, because I was getting a little bit muddled in some of the formulae, and I was thinking about if you could find out for n, or like if you could find n from thinking about the expected value of like over time, or the expected value of the
so the
like
number,
the coalescent time, I think.
yeah. So the first, right? The chimps and humans are not currently the same population.
Okay.
So there is very little chance any of us have a common ancestor with a chimp before the common ancestor with each other. In fact, I think we would all go as far as saying there is a 0 probability just about that any of us have a common ancestor with a chimp more recently than with each other. That turns out not to be true for a few regions of the genome. Some of us, for like our HLA allele, are more closely related to a chimp than we are to each other. But for almost everywhere in the genome, we are more closely related to each other than we are to chimps. So thinking about these models that imply that we have equal chance of sharing a common ancestor last generation is just false for most of the history between us and chimps. It wasn't false probably at the very beginning. At the very beginning of the evolution between humans and chimps, there's sort of one big population, and some people gave rise to chimps, other people gave rise to humans. So for a while, there was a little bit of what, if you're Matt Hahn, you might call lineage sorting or something. But for our purposes, we'll largely ignore the fact that there was a bit of time when humans and chimps were one big population. But since then, the way you might want to visualize the difference between humans and chimps is, say, with this picture. So this is the human coalescent, and the average time back to the common ancestor of all of us is 4n generations. And if n is on the order of 10,000, all of us on this call shared a common ancestor, about, maybe 40,000, 80,000 generations ago. So maybe 400 to 800,000 years ago. So all of us talking to each other probably had a common ancestor at any locus you're looking at a really long, a long time ago, like hundreds of thousands of years ago, but incredibly recently in comparison to when our ancestor was with the chimp. So if we add one more sequence out here of a chimp, all of these sequences coalesce within about 400,000 years, say. And then we go back 5 million years, way off the top of the page, and then come back another 5 million years, way off the bottom of the page, right back down to our chimp. So that we can sort of think of all this evolution from our common ancestor back down to the chimp as the vast majority of it, there was effectively a single lineage going on. That there is you can sort of think about it as if there is just one human in just one chimp, because humans have only been segregating for, say, the last few 100,000 years. And the same thing for the chimp, but the time back is 5 million. So we are largely ignoring this little bit of segregation when we're estimating the mutation rate between humans and chimps, thinking about it as if it were just a single sequence. Does that make some sense to you? That you could get a different estimate if you accounted for the fact that there's variation here and there's variation in chimps, but that estimate will be not very different, because for almost all the time between humans and chimps, the coalescence of chimps and the coalescence of humans had collapsed to a single individual. Other questions? Does anyone want to talk about homework 5? Has anyone looked at it yet? All right. When you look at homework 5, you're going to think I am trolling you. Homework 5 is homework 3, where instead of pulling an allele with probability P, we pull an allele with probability P times a constant. And you get the same answer as homework 3 over and over and over and over again, multiplied by the appropriate constant. And I'm going to have you do it with a constant. And then I'm going to redefine that constant in terms of another constant. And you get the same answer. And I'm going to redefine that in terms of another constant. You get the same answer. And I'm going to define it in terms of another constant. You get the same answer. And then you're going to have a formula that is the first formula Gillespie presents in the selection chapter. And what you will have derived is the expected frequency of an allele next generation under this arbitrary model of natural selection is some kind of uglyish formula. And that uglyish formula is nothing more than what you started with for neutral sampling and multiplied by a constant, and just that constant got uglier and uglier and uglier to account for different things. But you might blow through the first 10 problems in 3 minutes and not have understood why are you making me say this? It's so obvious. If you think that, you have understood completely. But the point is, by the time you've gotten to problem 10 or 11 or so, you're starting to write down all the key formulas that start at the beginning of Gillespie's chapter that look like they were given to you from God. They were not. They are simply binomial sampling, where the probability of picking an allele isn't its frequency, but a function of its frequency. Really often just a constant times its frequency. And you will, so we are going to see, we're going to derive all the key results about natural selection as simply nothing more than the expected frequency of an allele under binomial sampling next generation. When I pick it, not proportional to its frequency, but proportional to its frequency times a constant. And you will not believe how easy the first few problems are if you fully understood them. You'll think, I'm like, why am I bothering to make you say this? until you've worked your way down to what amounts to Gillespie's Formula 1 and or Formula 2 in chapter 3. And then like the problem after that will be this boatload of algebra to derive Gillespie's next equation. And then we'll start applying some of this stuff. But the reason I'm having you do all this is so that natural selection becomes hopefully intuitive in your mind as not something mysterious, not something, like even biological. Natural selection is nothing more than picking an allele for next generation at a probability different than its current frequency. Anything that causes that to happen is selection. If you pick it proportional to its current frequency, that's neutral. If you pick it proportional to any other frequency, that's selection. And we can probably analyze that model of selection relatively easily in terms of how it changes the probability an allele is picked for next generation. And much of the key results in natural selection are going to be super duper unbelievably easy if you think of them as just the neutral result with the probability modified appropriately. And that if you get into this field, that might be how you want to approach a lot of problems. Start with the neutral result, modify the probability, see where you get. Does that make sense? So if you blow through the homework and it takes you just like 15 minutes, you didn't do it wrong, probably. You completely understood. And if you think I'm being weird, you're right. I'm not justifying anything. I have no idea why I've written this constant is this, that constant. Why on earth? What is any? When you get to problem 10 or so, it will now be in a format that looks like Gillespie's book. And hopefully you will have understood it along the way. It was just this thing divided by that thing, this thing divided by that. You got it. Cool. Any questions? Right, so Tuesday I'm out. You guys can meet and talk amongst yourselves if you choose, or you don't have to, you can do whatever you like. But we'll be here next Thursday to talk about the homework 5. Questions? See you next Thursday.